Rebonjour ou bonsoir à ceux qui nous rejoignent pour la conférence du professeur Daniel Dennett, qu'on est fiers, honorés et très très heureux d'avoir aujourd'hui parmi nous. You cannot hear me? It's too much noise. Et comme je le disais ce matin, il est une des causes distales de notre présence aujourd'hui ici, puisqu'il a vraiment joué un rôle très important dans le rapprochement d'une série de disciplines, dans la mise en place d'interrogations aussi, dans des termes qui permettent le travail interdisciplinaire. Et de ce point de vue conceptuel, vous avez joué un rôle absolument fondamental. Et pour toutes ces raisons, enfin voilà, on vous remercie infiniment. Une des choses que j'ai remarquées aujourd'hui, du point de vue comportemental, c'est que quand même vous avez eu tort pour quelque chose dans votre carrière. Je me souviens de l'exemple que vous donnez de cette... ça rejoint la conférence de Redouane tout à l'heure, de cette... J'ai oublié le nom de cette plante marine qui tant qu'elle se déplace, a besoin d'un cerveau, et à partir du moment où elle trouve un emplacement, la première chose qu'elle fait, elle se mange son cerveau parce qu'elle n'en a plus besoin une fois qu'elle est fixée à un endroit. Et vous faisiez cette analogie avec les gens qui obtiennent un tenure. Le jour où ils obtiennent un tenure, ils n'ont plus besoin de réfléchir. Vous êtes le contre-exemple parfait. Je vous ai vu toute la journée réfléchir, reprendre vos slides et revenir. Et c'est magnifique. C'est un magnifique exemple pour nous tous. Et merci infiniment d'être là parmi nous.
Merci beaucoup, Fabrice. I'm going to speak in English. I apologize, but I think it would be painful for you more than for me. I will try to make up for it with my slides, and I've been revising them all afternoon to try to include some responses to some of the excellent talks that we've heard. So let me get going. I'm going to begin. I just want to do a little experiment so you know what I'm talking about. So you're probably familiar with this sort of phenomenon. I want you just to stare at the white cross. Don't let your eyes move. Just stare at the white cross for a few more seconds. That's probably long enough. Okay, what did you see? Yeah. I'm sorry I have to use the American flag. I didn't have time to do a French flag. I could have, It is a little bit more interesting. I'm going to do it one more time because I want to draw your attention to whether or not you would be prepared to assent to these two sentences. I'm having a flag after image, and the lowest short red stripe is intersecting the black cross. Now, we're going to go back and see if that's going to be true. So again, just stare at the cross. And that should be long enough. Okay. So, how many of you would agree with those two sentences? Yeah, okay. Now, what are you talking about? It seems you're talking about something real and something red. Where is it? Is it in your brain? No. Is it on the board? No. Well, is it somewhere else? No. I think the lesson that every naturalist has to come to grips with is the answer is no, it's not somewhere else. And the question then is, how can that be? The reason this is a problem is well known to philosophers because of Leibniz's law of identity. Very simple. If A is B, then whatever is true of A is true of B. If B is blue, then B. If A is blue, then B is blue. If A is in Cleveland, then B is in Cleveland. If A is bigger than a red box, then B is bigger than the red box, and so forth. So if A is a red stripe and nothing in the brain is a red stripe, then nothing in the brain is identical with that red stripe, which has to be something else. That leads us to dualism. So the alternative, the only alternative to dualism is to say you are experiencing a red stripe, but there's no red stripe that you are experiencing. It only seems to you that you are experiencing a red stripe. That's a boundary condition on a naturalistic view of consciousness. And it's very hard to live with. Two artifacts made by two different species of animal. On the left, we have a termite castle. On the right, we have La Sagrada Familia in Barcelona, Gaudi's great church. Stunningly similar in appearance and even in construction and materials in many regards, and yet at the same time profoundly different in construction and in design. I use this contrast to draw attention to a very important puzzle and a very important difference between two kinds of designing activities. There's the termite's way of building that termite castle, which we might call bottom-up. And what's important about that is that there's no king termite or queen termite or architect termite or boss termite, and the individual termites don't have a plan in mind. They are clueless. They are not comprehending the larger scheme in which they're involved at all. They don't have to. This is bottom-up design and construction. Gaudí, in contrast, is the paradigmatic genius architect. He's got plans, he's got blueprints, he's got manifestos about why these are the things that he's doing. He is the epitome of the intelligent designer. The person who's got a blueprint, got a plan, got it all worked out, and is the big boss, directing the team below him. Two such different processes, top-down in the case of Gaudí, bottom-up in the case of the termites, yielding a very similar product. Now I've talked about this example in several recent papers, one in PNAS paper, and one the Cold Spring Harbor Laboratories publication during Darwin year. I talked about this. If you're interested, you find them on my website. But today I'm using them to underline a rather different point and a real puzzle. First of all, I want you to look at these amazing time-lapse pictures of neurons in action, groping around, hunting for better connections. You've got 200 billion, but who's counting, of those in your head right now. And here's the puzzle. How is consciousness possible? Human brains are basically like termite colonies, which are not conscious. I mean, the colonies aren't conscious. What is it like to be a termite colony? Nothing. And there might be 1 million termites. Well, there's 200 billion of those little neurons in your brain. Not a one of them is conscious. And that's all there is in there. How on earth do human brains achieve global consciousness, global comprehension, using local competences without invoking an intelligent designer? It's a different way of approaching the mind-body problem. And I have an answer. It is, I think, the only answer that's defensible. But it's very hard to make it clear to people. It's very hard to understand, and it's even harder to take seriously. My task now is to get you at least to entertain it, if I can make it clear what it is and let you see how it might be right. And my answer is this: by downloading virtual machines that give them superpowers. So 200 billion neurons, that's the hardware. Downloaded to that is software that gives it magnificently more powers than the hardware unadorned, untrained would have. Enough powers to create a conscious self, a Gaudí running on all those termites. That's the claim. Now I want to try to make that, if possible, comprehensible, if possible, palatable, and I'd almost be scared if I convinced you of it, because then you're too easily convinced. And I've been trying to sell this crazy idea to people for 20 years and more, and I'm going to try a different way, somewhat different way. What follows now is pretty half-baked. I've only been thinking about it in these terms for a few weeks, and I can't resist trying them out on you, because every time I discuss it with people, people come up with better ways of getting at it. So I am now using you to help me make this idea better. And I'll give you a little roadmap, and then we'll go through it. It's from ontology via affordances to Umwelt, from Umwelt and Hume's strange inversion to the manifest image and consciousness via Bayesian predictive coding. It's all in jargon. Some of you already know what it is. How many of you are up on the current bandwagon on Bayesian predictive coding? Almost nobody. Well, a few hands right up at the back. Okay. So, and I'm not going to spend much time on that, but it's that which has got me galloping off on this tack in this way. So I can sketch this out for you today. So first I want to talk about strange inversions, 3 of them, one of Darwin's, one of Turing, and one of Hume's. I've talked about the Darwin and the Turing so often that I will rush over that. Some of you will be familiar with this already. One of my favorite passages of criticism of Darwin came from this Robert Beverly Mackenzie, outraged critic back in 1868, and this is what he says: "In the theory with which we have to deal, absolute ignorance is the artificer, so that we may enunciate as the fundamental principle of the whole system that in order to make a perfect and beautiful machine, it is not requisite to know how to make it." The capital letters were in the original. "This proposition will be found on careful examination to express in condensed form the essential purport of the theory, and to express in a few words all Mr. Darwin's meaning, who, by a strange inversion of reasoning, seems to think absolute ignorance fully qualified to take the place of absolute wisdom in all the achievements of creative skill." He's got it. That's exactly what Darwin was doing. And it is indeed a strange inversion of reasoning. It overthrows one of the most natural ideas that we have, especially in universities. Why do we send our children to universities? So that they can get the wisdom, so that they can have the competence to do all sorts of wonderful things. So that's Darwin's strange inversion. Turing had a very similar and indeed deeply complementary inversion, which I've discussed in print and will discuss again in print in an article called, surprise, surprise, Turing's Strange Inversion of Reasoning. 2009 was Darwin year, 2012 is Turing year. So I will be speaking fairly often about Turing this year. Here is a picture of some pre-Turing computers. They're wearing dresses. A computer was a person. This was a job description. Computers were people. They typically had studied mathematics. They certainly knew their arithmetic, and they understood quite deeply. This was a technical job, and they were hired by the thousands in industry to be computers. In the old days, pre-Turing, computers had to understand arithmetic. They had to appreciate the reasons. And what Turing realized, that this was just not necessary. That you could throw away the comprehension and just have the competence. Now let's see the parallel. Here's Darwin. In order to make a perfect and beautiful machine, it is not requisite to know how to make it. And here's Turing. In order to be a perfect and beautiful computing machine, it is not requisite to know what arithmetic is. And once you've got arithmetic and conditional branching, you're off to the races. That gives you a computable base. Every computer, that's all it is. It's just arithmetic and conditional branching. That's all you need. Together, they are both giving us a sort of double whammy, strange inversion of reasoning, and my bumper sticker for this is competence without comprehension. This goes very nicely into French, hein? Compétence sans compréhension. This is my new slogan. It is strange. We tend to think that comprehension is the source and the explanation for competence. This person is competent because she understands. And in their different ways, actually very similar ways, Darwin and Turing showed us how to invert that and recognize that you can have competence first and comprehension will come later. It will be an effect, not a cause. Understanding, mind, consciousness, intention is the effect, not the cause. Just the opposite of the way people tend to think. Now I want to add a third inversion from Hume. By the way, I love this picture of Hume. It's in the Edinburgh rector. The University of Edinburgh has this portrait in his office, and I was there recently, got to stand beside it. And I'm looking for one of those pink hats. If I can find one, I want to wear it. If anybody knows where I can get a pink hat like that, let me know. So here's Hume's strange inversion. It's only recently that it occurred to me, oh my gosh, I think probably Darwin, Turing, and Hume are my three favorite thinkers of all time, practically, and they're all Brits. And I'd not thought that what was so great about Hume was that he had his own strange inversion, but he did, and it now looms in my mind as really important. And it's about our experience of causation. Now, I think when I used to teach this, I haven't taught it for years, but I think when philosophers teach this, they often overlook what's really exciting and interesting about it. Hume says, here's where we get the idea, he says, the idea of necessary connection between cause and effect. He said, first, we see A's followed by B's, A's followed by B's, A's followed by B's. First A, then B, first A, then B. We see this quite a lot, and it develops a sort of habit in our mind. We expect, when we see an A, we expect a B. He's way out ahead of Pavlov here, but that's basically what he's discovering is classical conditioning. But then the really interesting part is what happens next. he say, after we've seen this for a while, we have an expectation, and it's a feeling. There's a feeling there's a bee coming. And then, this is the genius part, he says, we then misinterpret this internally generated, subjective, even sort of emotional feeling as an impression of causation from the outside, caused by a perceptible property of the external world. This creates the phenomenology A causing B, and we think we can see the causation. That we have an impression of causation directly. We have an impression of A, we have an impression of B, and we have an impression of A causing B. And he says that's a mistake. There is nothing out there in the world that you can see, nothing that is causing you to believe that A is the cause of B. You believe that A is the cause of B because you've experienced A is followed by B's, A is followed by B's enough so that you now have this association which creates this feeling which you then project out onto the connection between A and B. In other words, he says, you're turning judgment and phenomenology inside out. The reason it seems to you that A is causing B is because you judge that a B is coming. Not you judge that a B is coming because it seems to you that A is causing B. You've got the causation just backwards. So again, Hume's inversion is like Darwin's and Hume's. Hume's inversion is like Darwin's and Turing's in that it inverts a sort of causal order that we just take for granted. Now, this projection is an irresistible metaphor. I think I've already used the word. It seems that we project the feeling out and attach it to the object. So I've just given you Hume's example. Now I'm going to give you a few others. Whoa, what? I got something out of order here. Okay, well. Oh yeah, here it is. It's not the case that we like honey because it's sweet. It's rather more the case that honey is sweet because we like it. That's putting it a little crudely. But let me just spell it out a little better than that. Here's the pre-Humean, pre-Darwinian idea. First, there was sweetness, and then we evolved to like sweetness. No, that's just wrong. That's just getting it backwards. That's the pre-Darwinian vision. Sweetness was born with the evolved wiring that made us want it. So, there's glucose. Theorizing about sweetness by looking very carefully at the structure of glucose is hopeless. You won't find the sweetness in the structure of glucose. It's not there. It's not an intrinsic property of glucose. You won't find the sweetness out there. You need to study the brain and the evolution of the brain to understand the existence of sweetness. Sweetness exists because glucose is high-quality energy, and any organism that has a preference and is willing to devote some time and energy to acquiring this is on the right track. That's why honey is sweet. That's why glucose is sweet. Sweetness is the effect, not the cause, of our desire for sweet things. So let's just look at the pre-inverted history, the old-fashioned, the mistaken history. God sees that we should adore glucose. So he sprays glucose with sweetness fog. You know what that is. Which causes people to experience sweetness. Which causes them to decide they love those sweet things with all that glucose in them, with all the sweetness fog on it. And that's how God made sugar sweet. No. There is one cause too many. Cancel the sweetness fog. We don't need the sweetness fog. God, cut to the chase, he simply arranged for glucose to trigger the labeled desire, the sweet, yummy desire label, which was wired up to initiate, provoke, and intensify the getting behavior, and he's home free. It's just as Hume said about causation. We project the experience onto the sweet things and think, ooh, they have this intrinsic property of sweetness, which we just love. And it causally explains our desire for it, why we appreciate it. No, there's nothing out there in the glucose by itself intrinsically that causally explains why we like it. That's getting the order of explanation backwards. This is, I would say, a benign user illusion. We know what sexy is for. It rewards us for all the time and effort spent mating. Now, it's a dirty job, but somebody's got to do it. There's nothing intrinsically sexy about this, which is a good thing, because if there were, evolution would have a problem. How to get chimps to mate. Well, here's one possible solution: hallucination. But there's a simpler way. Just wire up the chimps to love that look, which they apparently do. No intrinsic sexiness, just being wired up to go for the right sorts of things for your kind. Another inversion. It stands to reason that we adore babies because they are cute. And again, it's the same sort of thing. This is, and we think naively that because we find them cute, we want to cuddle them and care for them. Whereas, in fact, it's because we want to care for them and cuddle them that we categorize them as cute. Now, we can study as people have, the geometry of the face, which seems to be the important trigger here. Jack Horner has even argued, with some plausibility, I would say, that some species of dinosaur were altricial, that they were cared for by their parents. It's unusual in, egg-laying creatures, because those dinosaur babies had those foreshortened, cutesy faces. And that already in dinosaur times, cutesy, foreshortened faces were the trigger for nurturing behavior. It's perhaps a straw in the wind, but an interesting straw. It's just about backwards. Okay, so now there's the three strange inversions. So now we're ready to go back to my story from ontology by affordances. So now I want to talk about ontology, which we heard about earlier today. We heard about ontology from Lawrence. And Lawrence, where's back there somewhere, and Fabrice. Okay. So I put in these slides to comment on them. Several years ago, I was thinking about content and ontology, and I decided to develop an example at rather more length than you might think necessary. But bear with me, I think there's a punchline to it. Back when I was a child, there were elevator operators. These were people. Rather like computers were people. Well, elevator operators were people. And they had to be trained. And I went looking around on the web, and what did I find? But the training manual for elevator operators. Back in those good old days, this is actually, I think, an Army training manual. And I'm not going to go over all the details. But this is the book of represented rules and represented rationales for the rules for how to run an elevator. So now what I want you to do is to imagine, we don't need to go into the historical details, but of course those are all gone. It's all been embodied in hardware, little chips that run our elevators today. So how did this process of automating the elevator go? So here's a little sort of just so story, which is going to talk about what actually must have happened. I don't know the historical details. So some client wants automatic elevators, has got the elevator rules that they've been training using with their human operators, takes this to the Acme software company and says, please, can you take this rule book and sort of reconstitute this performance, this competence in one of your software devices? So they look at the rules, and first thing they do is they turn it into pseudo-code, where you can it's just sort of translating it halfway into source code. And this is a useful pedagogical move, self-pedagogical move if you're writing software. So they turn it, and if you don't have to know computer programming to sort of look down it and see, oh yeah, I see. Let's see, if car empty, then go fetch. If call input, then I just sort of made this up as a little bit of pseudocode. And it actually gets quite complicated if you have complicated elevators, or you have whole banks of elevators, and you don't want them being redundant, and who's going to get the guy on floor 5 and so forth. But it goes from pseudocode, and then from pseudocode you turn it into source code, which is what can be compiled and go to your computer. Now, source code is still quite explicit representation of rules. There's a little source code. This isn't elevator source code, but it's just some source code I just used. And you'll see that there are comments embedded in source code which tell you the rationale. This is why we're doing this. This is aid to future programmers, or to yourself when you're debugging your program later. You put these comments in your code to remind you what the raison d'etre of that particular bit of code was. Yeah. Now the program doesn't read those. Once it's compiled, the comments are just skipped right over. By the way, that has a delicious parallel in evolution, in genes, in genetics. Feral pigs, feral sheep revert to their wild state very fast, just a few generations. They're right back to their old phenotypes. They're close to it. What domestication has done, instead of erasing all those genes, it's just commented them out so that they don't get expressed. They're still in there, they're just commented out. And it takes just one mutation to take the parentheses off, and then boom, you get those genes right back. So in both cases, it's the same thing. You've got information that is suppressed, but is still in there and can be recovered. It's a lot cheaper and quicker than erasing, and then if you ever need it in the future, you got it. But so we've got some comments here. But they don't play any role in the execution of the source code. That's important only for those people who think that they want to follow Jerry Fodor and his idea about what Turing's ideas are. Jerry's got it, I think, just backwards. That's Jerry's strange inversion. But we won't go into that here. Now, source code, as I say, is still quite explicit representation of rules. I've mentioned commenting, okay. The comments are inert. Now, when you compile the code, the rules all but disappear. Compiled code is just, here's a bit, 0, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, and so forth. A few trillion of those. That's what compiled code looks like. It is almost impossible, but not sometimes close to impossible, to decompile code, to go back to the source code. Some people can do it some of the time, but it's a real chore, because by the time you've got to compiled code, it's quite inscrutable. Why is that important? Because once you've got the compiled code, the rules are nowhere explicitly represented in any interesting sense of explicit. And yet, the rules that you worked so hard to get in the right shape in the source code so that it would do the job you wanted, they work beautifully. So the elevator, you put the compiled code on a chip and you put it in the elevator is perfect. It does exactly, it follows all the rules you told it to follow, but those rules are now submerged. They're not evident. They're not, you can't say, and now the elevator is consulting rule 7. I mean, you can say that, but the only reason you know that is because you know what the source code was and you figure somehow or other this is getting accomplished right now. It's not evident at all in the actual operation. Now, we theorists and observers from the outside can see that a certain ontology is well exploited by the elevator designers. If they've done their job right, they've got the same sort of categories that had to be understood by those elevator operators when they were running the elevators. They had to be able to tell, you know, a person from a box and a call from a mosquito and know whether the doors are open or not. Now, we might say that that's the elevator's ontology. But of course, an elevator isn't an organism, it isn't an agent. We might just say, well, no, it's the engineer's ontology. And that raises a really interesting question. The engineer's perspective, they're saying, what discriminations do we need to make this thing do what the client wants? Well, we have, instead of counting people, we'll probably use weight, put a scale in the floor of the elevator. We want to know if somebody's calling for the elevator, is the door closed? They make a list. These are the things that have to be discriminated by transduction of some kind, by transducers. And then they say, now we've got all the categories, the discriminations we need, we have to put them together. What are we going to do with those? This gives a certain amount of content for the subject, if the subject is the elevator control system. This is its view of the world. It's very limited, but it's very effective. This is all it needs to know to do its job. This is all it needs to know to do its job, because of course it doesn't really know anything. It is competent without comprehension. I'm going to say that that's the system's Umwelt. Now that term Umwelt, I'm using it in the sense of von Uexküll, who talked about the Umwelt of even very simple animals. What was in their sort of behavioral ecology? What was their environment? What was its ontology? And blessedly, he didn't worry about whether they were conscious. He just realized that even sea sprites are competent. They have a sort of Umwelt, and it can be described, or you can describe the Umwelt of a starfish or a lobster, or heaven knows, of a grouper or a chimpanzee. And in the case of natural agents, unlike my elevator operator is an unnatural artificial agent, of course. There's a rationale for the design of the system, and it's probably close to optimal given the time that's been available for evolution to do its work. So it would seem that even since elevators aren't really conscious, not even Dennett thinks elevators are conscious. So there is what I would call a subpersonal level to the elevator, and I've just sort of described it to you. Is there also a personal level in the elevator? And I say no, there really isn't, not really. But there is something which plays a very similar role, and that's the user illusion that human beings have when they use the elevator. They know that they can tell the elevator what they want, and they have to do it this way and that way, and then they have expectations. They adopt the intentional stance towards the elevator, and it works just like a man did. It works very well. The elevator has the competence, and they don't need to understand how that competence is executed, but they do need to have a robust, easy way of anticipating what the elevator is going to do next and why. So there is a user illusion, and that creates a sort of, you might say, a bogus personal level for the elevator. Okay, so much for ontology. Now, affordances to Umwelt. As I said, Umwelt doesn't imply or require, let me just go backwards, consciousness. I'm skipping over a discussion of Gibson and affordances because I'm going to assume that people in this room pretty well know that story. If I were doing this properly, and maybe in another version of this talk later, I'll have a picture of Jimmy Gibson and I'll have a little section on affordances and what they are. But they were mentioned several times today. Good. So I'm just going to go on and talk about Umwelt and how we get from Umwelt via Hume's strange inversion to all the way to the manifest image and consciousness. We're going to get a little closer to that goal of how can that termite colony of a brain have a personal level and be conscious. Now, the term the manifest image is, of course, due to another one of my heroes, Wilfrid Sellars, in his wonderful paper, Empiricism and the Philosophy of Mind. He distinguishes the manifest image from the scientific image. The manifest image is the world we live in. It's solid objects and colors and all the folk physics and folk psychology and naive sociology of our world. That's the manifest image. And Sellars famously says, and I agree, and I am exemplifying that agreement right now. Sellars asks what philosophy is, says, philosophy is trying to say how things, in the broadest sense of things, hang together in the broadest sense of hang together. I think that's about right. More specifically, I think that philosophy is negotiating the registration of the manifest image with the scientific image. How can we put these two visions together? Two ways that don't work. There are scientists who say, strictly speaking, nothing is solid, and there are no colors, and there is no consciousness, and words don't exist, and colors, strictly, all there is atoms, or quarks. Well, we know what's at least deeply misleading about that. We should also discard its mirror image, which is the person in the humanities who says, science is just a myth. It is just a religion of a certain group of overpaid smarty pantses. That's also wrong. The fact is that science is the best ways we have of getting the truth on all subjects. I will endorse that claim. But it doesn't answer questions about the manifest image well, and that's where philosophers have a lot of work to do. And it doesn't go gently. We've tried all the simple identity theories and the simple just line up point A and point B and everything falls in place. It just doesn't work that way. There's accommodations and negotiations and even sort of diplomatic efforts that have to be made so that you can see how to translate, and translate is even too strong a word, the facts about color in the manifest image with the facts about electromagnetic radiation in brains and so forth. Okay, so the manifest image includes preeminently affordances. I don't know if people have made this point, but Gibsonian affordances provide the furniture for the manifest image, and that's why different organisms have different manifest images, because my favorite example for years has been both anteaters and birds that eat insects, that are insectivorous. Insects enter into their manifest images, but in a very different way. The bird that catches flying insects tracks individual insects, and has as a result a higher flicker fusion rate than other birds. It sees faster. its film, in effect, runs not at 30 or 60 frames a second, but maybe 100 frames a second or faster. The anteater, on the other hand, just sweeps up with its big sticky tongue. Ant is a sort of mass term, have some of that ant. And it no more distinguishes individual ants than we distinguish individual water molecules when we drink water. So different manifest images go with different talents. So affordances are the principles that populate our manifest image. So sweet, sexy, cute, funny, these are all part of the manifest image. Colors, solidity, causation, billiard ball type causation is very much part of the manifest image. Free will and, of course, other minds. All of this is part of the manifest image of Homo sapiens. And interestingly, in almost every case, there is a projection of a property that is properly internal, that is affective. I've given you several examples. Earlier today, Julie Grez had one line that emotions are action tendencies. Yeah, and so are affordances. They are, in every case, they are anticipating doing something about it. And when I remember Hume's strange inversion is that we misinterpret an inner reaction as an outer cause. So here's how, and as it's very tempting to say, we project it into the manifest world. That's what Hume said, and that's what it seems that we want to say about sexy and red and sweet and all these other cases. Projecting is the most natural metaphor, but it cannot be literal. It's another one of those constraints of naturalism. The impression of causation is not being beamed out through your forehead onto the causes and effects in the world. Projection is a delicious metaphorical characterization, so we have to replace that metaphor. What does it mean literally? What can it be that's really going on when we project these properties? Here is where Bayes, yet another very clever and useful Englishman, comes along. Bayesian predictive coding. I am not going to spend any time doing a primer on Bayesian statistics or Bayes' rule. I'm just going to leap ahead and say what Bayes showed us was how to think about an organism that has to take its existing, where it is now, its prior knowledge, its current set of how the world is, and use that to lever an anticipation of what's most likely to happen in the future, and to sort of make a bet on the future, which then you can then check to see if your bet is right, and you can then adjust your prior probabilities to deal with that probability and so forth. And the Bayesian perspective is currently being explored in very interesting ways, and I'm caught up in that enthusiasm to some degree. I'm trying to keep my feet on the ground. But it's something that I've been talking about for years anyway. The idea is that brains, the main job of nervous systems is to anticipate the future. In fact, even the main job of the protein networks in single-celled, in amoebas, they don't have a nervous system, but they still have chemical networks in them whose job it is to prepare that little amoeba a little bit better for what's going to happen next than it otherwise would. It has a future horizon which is just minuscule, just milliseconds. But if it can anticipate its own future a tad better than the competition, it'll do better. And so even the lowly amoeba is brilliantly designed by over 1 billion years of evolution to be on the lookout all the time for how to make its life a little bit better. Like those neurons that are groping around in the brain, trying to improve their lot just a little bit. Every affordance yields a predictive action tendency. And that sets up a sort of forward model, as an engineer would say, an expectation of how things ought to go in the immediate future. Now, here's my Hume-inspired claim. We read that forward model backwards, more or less, and we see that as creating a property. This adds to the ontology of our control system in the following way. We're designed by evolution to perceive as many affordances as possible. We should have anticipations about everything that matters to us. People are pretty much in agreement about that. Among the things that matter to us is ourselves. And everywhere we go, there we are, an important part of the environment. And if we are wrong about what we're going to think next, what we're going to do next, we're in deep trouble. So we should have, in addition to our expectations, we have expectations about our expectations. When we see a baby, we not only feel the urge to reach out and cuddle and so forth, we expect to feel that urge. When we recognize it, it doesn't surprise us. Why? Because it's so cute. And so we're already, our expectation about our own expectation is fulfilled. See, check it off, check it off. So in the same way that Bayesian predictive coding says that, as I'm sure you know, there's more downward traffic in your perceptual system, in your visual system, than the upward traffic. There's more stuff coming down, and the predictive coding hypothesis says your brain is constantly anticipating what you're going to see next. And as long as the anticipations are fulfilled, nothing happens. The only signals that get sent back are when there's surprises, when things don't go the way you expect them to. So, I'm suggesting that our satisfaction of that expectation, we interpret it as confirming our perception of cuteness in the baby. And that's what objectifies cuteness as a property. So it's the satisfied expectation of our expectations is the literal truth that gets metaphorized as projection. Now, I'm going to drop a shoe. I'm going to talk about Ned Block, because originally I was going to talk about Ned Block and his, I think, forlorn attempt to distinguish access consciousness from phenomenal consciousness. And I'm going to be short and sweet and probably unfair. But then there will be a chance to undo that later. I've been talking about this with Ned and without him for a long time. I'm going to tell you a true story of an event that happened some years ago. Ned and I were having lunch somewhere, and we were talking about laterality differences, left brain, right brain. And one of the standard laterality tests is where you, as a subject, you look at a cross on the screen, and either a word or a non-word flashes in either your left hemifield or your right hemifield. And the task is to say word or non-word as fast as you can. And if you're strongly lateralized to the left, that is your left hemisphere, most of us are. I'm left-handed, so I'm actually mixed. But if you're a right-hander, then you're strongly lateralized left for words, which means that you respond much more accurately and much more quickly to words in your, you have to do the crossover, in your right hemifield. So we were talking about this, and Ned had just undergone the test. I'd done it sometime a little bit earlier. And I said, so Ned, are you strongly left lateralized? He said, yeah, in fact I am. And then he said, tell you what, the words on the left appeared blurry. And I said, very interesting, Ned. What I want to know is, which is it? Did you have trouble seeing the words because they were blurry? Or did they appear blurry to you because you had trouble seeing them? And he recognized that he didn't know how to distinguish those two cases. Was his conviction retrospectively that the words appeared blurry, was it caused by his inability to identify the words, or was his inability to identify the words caused by their seeming blurry to him? He couldn't say. And I think that's very important. So here's Bloch's uninverted reason. He has a pre-Darwinian, pre-Humean, pre-Turingian view of the causation in the mind. He thinks phenomenal consciousness is the causal basis of access consciousness, while in fact it's an effect of access consciousness, not a cause. He's got it just backwards, but in an ancient tradition. I mean, this is what the pre-inverted thinking tends to be. Okay, now finally, ready to say a few words about downloading virtual machines that give superpowers to this brain which is made of neurons. This is really a huge step of imagination, and I want to just compare it with other attempts. Descartes' solution, of course, was an immaterial soul, which was, I've argued, not really a solution, but a tarted up evasion of the solution. Since an immaterial soul can do whatever you say it can do, it doesn't really explain a thing. And so my naturalistic solution is an informational soul, a soul made out of software. Not Cartesian dualism, but the dualism of hardware and software, which I submit is not offensive at all. So now, how could an informational soul evolve? I've got a lot to say on this. I'm just going to give you a few hints, and you can then be outraged. Words are virtual machines. What is a word made of? Not ink, not sound. A word is a very complex and sophisticated informational structure. It is a behavior organizer. My wonderful colleague Ray Jackendoff, in his brilliant book Foundations of Language, calls words, or lexical items, semi-autonomous informational structures. And I think that's about right. They can leap from language to language. They have many roles to play in cognition. And I want to take that dead literally. So words are semi-autonomous informational structures. In other words, they're like Java applets. Now, Java applets, the amazing thing about Java applets is that the wonderful thing about Java is that you can write a Java applet, you don't have to know the hardware that it's going to run on. It'll run on a Mac, it'll run on a PC, it'll run on a Unix machine. And it's not a mystery why this is so. In each case, your laptop or your computer has downloaded the JVM, the Java Virtual Machine. And then the Java applet runs on the Java Virtual Machine. And you go on the web. Mostly this is completely transparent. You don't even know it's happening. How many of you have ever, in effect, noticed that your laptop was downloading a new version of the JVM? Most people. It's happened, believe me. If you're on the web, you've done it. You know, they keep making little changes. The JVM is a nicely invisible tool that permits people anywhere in the world to write software that will run safely and well on your computer, no matter which kind of a computer it is. So now, today, I've been counting on you to have downloaded, one way or another, the EVM, the English Virtual Machine. I am only halfway in the midst of downloading the FVM, the French virtual machine. Once you have one of these VMs, which are analogous to the Java virtual machine downloaded, then you can instantly take on new competences by simply downloading a recipe for making cherry pie, or a new way to play a game, or any of 1,000 other things. As you know, when they experiment on animals, monkeys for instance, and they want the monkey to perform some test, it sometimes takes them thousands of training trials to educate the monkey into how to do the task. With the human subject, you say, here's what I want you to do, and you're going to be paid $5 an hour, you do this, you do this, you do this. 2 minutes later, give them a few practice trials, and they're going to be as good as anybody could ever be at that task. They take on this virtual machine task effortlessly and immediately, and they can now, they've expanded their competence just stunningly. There's a big difference between Java applets and words, and that is that nobody designed words. Nobody. Evolution designed words. A few people sometimes coin words, but most attempts at coinage fail, and when you succeed in coining a word, your role is infinitesimal anyway. And it's cultural evolution, it is not genetic evolution. Words do not evolve by genetic evolution, they evolve by cultural evolution. Then there have been genetic reactions. I'm sure that our brains are much better at being language users than the brains of our ancestors when language was first getting going. Terry Deacon has a lot of good things to say about that. Well, how do we install as virtual machines in us? By repetition. My grammar school teacher used to say, use a word 3 times and it's yours. And you know, she was basically right. There's some lovely empirical research now by Deb Roy, and you can see it in the spectacular TED Talk of last year that he did. Deb Roy, R-O-Y. He, only a guy at MIT could do this, would do this. Before his son was born, he got a mega grant, wired up every room of his house with fisheye lenses, video lenses above every room, and built a data farm to download every waking hour of his child for 3 years. And they now have this incredible database, and they can tell how many times the child heard a particular word before the kid tried to say it. And they've got wonderful things they've discovered about patterns in this. It's not very many, 5, 6 times, and then of course it gets shorter. So the installation of words in a brain is a matter of repetition, but not as much as you might think. And in fact, even one-shot learning, I think, is often concealed repetition. It's rehearsal in your own mind, and each one of those counts as a trial. So if we want to be Humean associations, we can say first A, then B, first A, then B, then first A, then B, and we can entrain a little loop that does that, little practice loop that runs in our head, and build it up like that. Words make possible the recessive transmission of information. This, I think, is one of the keys to culture. People are duly eloquent on how magnificent language is in the comprehension department. Language comprehension is one of the great triumphs of the natural world, that such a thing could exist. But I want to point out that almost as important as comprehension of language is transmission without comprehension. I'm going to do another quick experiment. I want you to repeat after me. Are you ready? Mundify the epigastrium. Again. Once again. Perfect. Do you know what it means? You don't have to. You don't have to because you've downloaded the EVM, which automatically sorts what the sounds you heard into a finite alphabet of phones, which are very easy to store and recall. It's digital. It's digital. Nature discovered digitality long before computer scientists did. To prove that, I'm going to give you another example. So again, repeat after me. Are you ready? No? No? The acoustic signal was just as loud, just as strong, had just as many bumps and ups and downs, but you didn't have the EVM to parse it into its phone, so it's unreproducible and unmemorable. Whereas Mundify the epigastrium is almost unforgettable now, even without knowing what it means. If you're curious, my mother used to have a lawyer who used to show up at our house around about 5:30 or 6 in the evening, and he would say, much in the matter of, who's the comedian? W.C. Fields. I think it's time to mundify the epigastrium, by which he meant he'd like a shot of bourbon. Mundify the epigastrium officially means to soothe the lining of the stomach. Why bourbon raw would do that, I don't know, but that's where I picked that phrase up, see? Unforgettable. Words help us use and transmit information that we don't understand. The passing along from generation to generation of semi-understood language is really important. And I've written a lot about that elsewhere, but we don't need to worry about that. So, words, as virtual machines, create multiple micro-habits in our brains. And I'm just going to look at one simple micro-habit that you have in your brain, and then I want you to recognize that this is multiplied by thousands, and that this changes the power of your brain in all sorts of ways. All right, so what I'm going to show you is a stupefect. Now, what I want you to do is, first of all, just call out the colors of the rows of symbols. Are you ready? As quickly as you can. Okay? How about this one? How about this one? This one's easy for everybody who doesn't speak Greek. If you have the GVM, you have as much trouble with this as you have with that. This is, of course, a very well-known and simple example of a little set of dispositions that, for better or for worse, you have in your brain. They're sort of involuntary, and they shape your competences in 1,000 ways. And it is out of that set of competences, I claim, that the larger virtual machine of consciousness and the personal level exists. Thanks for your attention.